Okay, so our focus today has to be on Chapter 7, because Chapter 7, which is on virtual memory, which is, yeah, a little weird, and we'll talk about that in just a second. But it's on virtual memory. That is the last chapter that's going to be covered on the test next week. Overwhelmingly, more than 4-1, those of you who voted that you wanted it to be on Wednesday of next week, which is fine by me. That's fine as far as I'm concerned. But it'll be on Wednesday of next week, so it'll be done on Canvas as it has been before. I have not made the exam yet, but I feel confident saying that it'll be largely the same format as the previous exam. Okay, there's not much more that I can do other than that. This doesn't matter to you, but for those of you who may be watching on the video, that means that there will be no lecture on Monday. Yeah, so if you have questions as you're studying, then send me an email, and maybe we'll do an impromptu answer session or something like that on Monday. If I get enough questions and if enough stuff comes up, then we'll do something online perhaps. That's a possibility. But if I know you guys are not going to start studying until Tuesday night anyway, so that won't be a thing that happens. But if you have questions, send me an email and let me know. I'll try and answer it as best I can. Obviously, we're going a little bit more quickly through Chapter 7 than I wanted to. I think that my initial instinct was that we would do Chapter 6 in 1 day and Chapter 7 in 2 days, and I think we've done exactly the opposite. And I think that's okay because I think Chapter 6 actually takes more time than I initially thought, and Chapter 7 will probably take less time than I initially thought. But to help you internalize the information from Chapter 7, there's a new exercise out, Exercise 6, which has questions from the Zybooks exercises. And so you can work on those, and so they should follow those questions should follow the format of the book fairly straightforward. Okay. Any questions about that before we get started? Okay. So virtual memory. Virtual memory is more or less what we've been talking about all along. Okay. We have couched it in different terms. We have couched it in terms of physical address, right, which is memory that is in RAM, and logical address. Okay. But if you start to think about the group of all the logical addresses, then you've got virtual memory. Okay, so the definition of virtual memory is a collection of logical address spaces. Okay. And then the one wrinkle that we really kind of haven't talked about very much, which affects a little bit, is that each of which could be bigger than physical memory. Okay. And this goes back to something we've talked about before. We've gone back, we've said, look, the total amount of RAM that you're going to need to house all of your programs is you're never going to have enough RAM to do that. Okay. And what this says is the total amount that you need to house just one logical address space may exceed the total amount of RAM that you have. Okay, so we're gonna completely do away with the notion that that logical address spaces have to be. And I was careful never to say that they were necessarily going to be, but up until now we've been talking generally about logical address spaces being smaller than physical addresses or the physical address space. Let's remove that limitation. Okay. So if we remove that limitation, then virtual memory, right? Virtual memory might be much, much larger than physical memory. And virtual memory is the system for storing and loading and unloading the various pages, perhaps, question mark, likely, of logical address spaces. Okay, so this is an internal notion of memory that gets to be sort of like the shared hallucination between all the processes rather, and then the operating system manages that and maps it to physical memory, completely abstracted away from the user, from the processes, from everybody who gets to still think that they have the entire physical memory to themselves all the time. Okay, and from a user perspective, now the user gets to believe that they do have enough RAM to run all of their programs at the same time. Okay, it's not true. They don't, and the programs are not running at the same time, but they're multi-programmed, and so this is like multi-memoried. Okay, to use the same sort of nomenclature, we just call it virtual memory, so that we get to believe that we have enough memory. Okay. All right. Any questions about that so far? Where we're kind of setting up for today? Okay. So logical addresses in this system are called virtual addresses. A paged virtual memory creates a single large continuous address space per process. Okay. And a page in virtual memory with segmentation creates multiple large address spaces per process, each of which is paged. Okay. So we're using demand paging effectively, and this is a concept that we're familiar with, except we're using it at the next level of abstraction up. Okay, demand paging, and this is the idea that we only load the pages from virtual memory when we need them, when we need those specific things. Okay. Now, that said, that's not the same thing as me saying that if we're not using this page, it must not be in memory anymore. Okay. Certainly, we're not in a hurry to empty pages out of physical memory. Okay, unless we need space to replace those pages with something that does need access. All right. That's the driving factor. This is called what? This is called a page fault. Okay. When I look for a page, okay, in RAM and it's not there, that's called being resident. Having your page stored in one of the page frames in physical memory. If it's not resident, then this causes a page fault because the program that needs that memory now needs you to load that page, okay, into RAM, which means replacing something. And so one of the major engineering problems that we face with virtual memory is how are we going to go about deciding what pages to replace? Okay, because I don't know about you, but I can't tell the future, right? And if I could tell the future, that would make my life a whole lot easier, but I can't, right? I don't have a crystal ball. So how do we do the best we can? All right, is the question that we're going to keep asking. What's a good engineering solution? Yeah, so each page has a, what do we call it? I think it's called in the book a present bit. Okay, and that bit is set in virtual memory if that specific page is in a page frame somewhere. Okay, so if you know that, if you see that the present bit is set, then you know you don't have to load it. That's not going to trigger a page fault. But if the present bit is not set, then that's gonna load. That's gonna cause a page fault. All right, so the next major topic then is this notion of page replacement. Page replacement. How do we choose, right? Which page to replace? So the virtual memory is typically much larger than the available physical memory. That's what we said earlier. So page replacement is the act of overwriting a page in memory with a different page loaded in the disk. So overwriting into a page frame, right, with a page that's out of disk, that's off the disk. Okay? Why is it in our best interest, right? And this is maybe critical, maybe it's worth saying this specifically, but where is virtual memory? Really? Where is it? Like, where is that data? It's stored on the disk. Okay? It's stored on the disk. So, with that information in mind, why is it in our best interest to cause as few or have as few page faults? Or if you prefer, to do as little page replacement as possible? Why is it in our best interest to do as little page replacement as possible?
Because the complexity for finding something on the disk is very big.
Yes.
We try to.
Yes, and it's not the complexity for finding it on the disk. We know where the pages are on the disk, but the time it takes to seek to that location and then to load that location into memory is the bottleneck. The disk is the bottleneck. Like if you're looking for the thing that slows you down, okay, as a computer, accessing the disk into memory is the thing that slows you down. That's the thing that happens on the human time scale rather than at or near the speed of light. Okay? Spinning a disk is really slow. Reading from a disk is really slow. Even solid state drives are slower because than cache memory or RAM, because you have to go through the steps to use the drive itself. So you have to use the device manager or the driver. Yeah, the driver program. Okay, as an intermediary. So this is always going to be slow. This relies on using the disk, so you want to limit this as much as possible. Okay? So limiting that means replacing the right page. Okay? And how do we know what page to replace? We'll get to that in just a second. There's also the idea of writing out a modified page, right? If you loaded a page, that page might contain memory. It might contain data, okay, for the program, and that data got not only accessed, but it got updated. Okay, so if the data got updated, then you must write it back out, the modified version back out to disk, and replace the modified page, replace the version on the disk with the modified version, right? Because if you don't, then the next time you pull that page off of disk, you're going to get an old copy, right? But you can save time by not writing out unchanged pages. or unmodified pages. So we need to keep up with which pages have been modified. And so just like every page in virtual memory has a present bit, every page has a modified bit. Okay. So if you write to that location to a location in memory on that page, then the modified bit, the first time you write something, anything, the modified bit gets set to 1. Okay, and it's not reset back to 0 until the next time that page is read in. And that triggers the demand to write the page back out to disk, which slows us down, right, even more. But we have to keep consistent data, and that's the only way to do it under these circumstances. But if we don't, if we look at the modified bit and we say, look, that wasn't modified, there's no reason to write that out, we save time. Okay, that's pretty straightforward, right? That's simple. That's like day one of thinking about page replacement. You realize you don't want to write things out or read things in that you don't need. Okay. All right. So let's look at page replacement. Page replacement algorithms. Okay. These fall into 2 categories. Oh yeah, sorry. Thank you. Fixed frame and variable frame. And this really refers to the number of frames per process. Okay, number of frames per process. 2 worldviews that we can kind of build off of. The first worldview says every process should have the same number of frames assigned to it. Okay, that way, process A will never have the opportunity to override any important information from any of the frames that are being used by process B, right? And so you can see that simplifies our problem, right? What frame should I give process A? Well, it must be limited to the set number of frames that belong to process A. Okay, so I just have to swap out something from process A, not anything from any other process, right? That's what I might be doing with variable frame. Okay, so this is fixed, having a fixed number per process, and this is variable, having a frame set that can grow and shrink depending on the need of the program. Okay, this is more complicated, right? But this presumes that you're going to be able to pick a number that will be satisfactory for all processes to have. Pick a number of frames. It's going to be satisfactory for all processes. And that it kind of assumes about processes that they always roughly need the same amount of frames in memory no matter what they're doing. Okay? And they can get away with that. But that turns out not to be true about processes, because sometimes they're doing really memory intensive things or really instruction intensive things where you need a lot of memory or data or instructions in memory at the same time. And processes will go into and out of those periods of high memory access. Okay, and if you have a fixed frame, then the processes are more likely to thrash. Okay, so this might lead to thrashing. Okay, but it's also simple. This is complex, and it gives us the opportunity to avoid thrashing, right? By giving processes that appear to need more frames a larger number of frames than processes that maybe appear to be in a state where they need less memory. Okay, so no wasted page frames. Okay, all the page frames are being highly used and that are being accessed at a high rate over here, but it's much more complex. Okay, and if you have it's complex because you need to be able to figure out, hey, how many frames does this process actually need? Can I take away some of its frame set and give it to somebody else? Because if you do that wrong, then guess what's going to happen? Thrashing, right? If you do it right, you can avoid thrashing, but if you do it wrong, it's going to cause more thrashing. Now, what do I mean by thrashing? I like that word because you can tell it's bad, right? It's like someone drowning, right? Well, the prototypical example of someone drowning where they're like, help, 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 they're splashing around, that's what your process is doing, right? That's the mental image that thrashing pulls to mind. It occurs when you're constantly having to read in pages from disk. Okay? If you need all the pages that you have, okay, and then you need one more page, you got to pick a page to replace. Then you can run an instruction or two, and then, oh my gosh, I need all those pages that I had. All right? You got to go out there and pick that page back up and replace another one, right? In the worst case, you just don't have enough frames to your name to do what you need to do, right? Because you've been limited to the number of frames. So this can actually cause death to a program, right? You can just completely die, right? Not being able to finish executing. More often, you just spend more time. You spend more time reading pages into physical memory, into the page frames, than you do actually executing your program. Okay, and that's going to lead to obviously a notable slowdown from the user's perspective. All right, so let's look at fixed number frames first. No. Fixed number of frames. Okay. Oh, you guys can't see. Hang on. So there is, I'm just gonna list these and we're gonna go over them. The optimal replacement algorithm. There's the first in, first out replacement algorithm. And there's the least recently used replacement algorithm. Okay? And those all fall under fixed number of frames. All right? The optimal replacement algorithm is the algorithm that always has the page I need next resident in memory, in physical memory. All right? What's the problem with that? What's the problem with it? Always has the next page that I need resident in memory when I need to make that call. Right? What would it take to do that? Under circumstances where I know that my virtual memory is larger than my physical memory, okay? And so what would it take to be able to do that? It would take always removing the page that I am going to, removing the page with the farthest away, right, access, right? Where it's going to be pick the page out of all the pages that I have that it's going to be the longest before I need that page again. How do I do that? This is impossible. Okay? Can't do that. The only way I could do that is if I ran the program and kept memory somewhere about where all what the entire series of references is, right? And then I would need to remember that and run the program again, right? And that's just and even then that's only going to work under the same inputs, right? So I need to do that for all possible inputs, all possible machine states. Yeah. Well, obviously that's not going to work. It's going to require me to look up more memory than I have access to, right? So this is impossible. I cannot, there is no way for me to implement the optimal replacement algorithm for the simple reason that I cannot see the future. I am not a prognosticator. I do not have a crystal ball. Okay, that allows me to see what the future holds, right? So I would need to always be able to tell which of these virtual memory frames is going to be used the farthest time away, and I can't do that. Okay. So why even talk about this? Because this is the gold standard, right? All our other approaches are going to be measured against this one. Yeah. And so keeping the page fault down as much as possible effectively is what we're after. Okay, the number of page faults down. But balancing that with our other engineering concerns. All right. So here's our first approach at how to do this. This is the first in, first out replacement algorithm. Okay. What's good about this, okay, is that it's easy. You've got a some number of page frames. Okay. And under the fixed number of frames approach, it's a set number of frames for your process, okay? All I need to do is remember I loaded this one first. I can load them from like top to bottom. So I loaded this one, and then I loaded this one, and I loaded this one, and I loaded this one, and I loaded this one, right? And so I just say pointer, okay? Hey, this is the guy that's been in this is currently the guy that's been in here long enough. He was the first in, okay? So when somebody needs to be replaced, we'll replace this guy, and we'll move the pointer down. And the next page that needs to be replaced is this guy, because he's now the longest, he's been the longest in memory. And then this guy, and then this guy, right? And so it's just a single pointer is all that is really required. All right, that's easy. So what's possibly bad about this approach? What does this approach assume? Assume about the nature of programs. It intrinsically assumes that just because you've been in memory long enough means that the longer you stay in memory, the less likely you are to be needed by programs. Does that seem reasonable? Not really. You might be data that needs to be accessed all the time. Okay? And so this is just, yeah, it's easy, but does it work? Right? It's an easy approach, but it's not a particularly convincing approach, right? All we're doing is just kicking out old data. We're not doing anything to keep track of when the memory was used last, just how long it's been in the pages, or in the page frames rather. Okay. All right. So gold standard. Straw man. You guys familiar with that term? So it's like an example of something that doesn't work. Okay. Just like a simple example, basic approach doesn't work. All right, here's what would work. Least recently used replacement algorithm. Okay. What does that sound like? How does it sound like that would work? Just out of the name, least recently used.
Like we navigate to the right, that's never referenced for a long time.
Exactly. Okay. So we keep track. We keep track of who has referenced, who's been referenced. Okay. And we need some kind of way, right, to keep track of the last time that each page frame was referenced, or the memory in each page frame was referenced. Okay. Or I guess you could say that each page was referenced. So what I can do is I can build a queue, okay, which is a queue, as you'll recall, is a first in, first out data structure usually. So it looks a lot like this, okay? This queue loads in all the page frames, okay, to begin with, right? And then if, let's say this page frame was referenced, okay, every time this page frame is referenced, you move that page frame to the back of the queue, okay? And so when you do this, you know that the guy at the front of the queue has been least recently referenced, okay? And so he should be the one to be replaced, and then the new page will be put in the back, okay? So as those, you can think of them as pages, as those pages move up in the queue, right, it gets to be that the one up front is always the least recently used, and so we should replace that page frame whenever we need to replace a page, okay? That works great. That's a great approach. The downside is it's expensive, right? It's expensive to keep track of every reference for every page. And every time I look up something in memory, okay, I need to modify this queue, right? So if you want to have absolutely the best possible approximation of the optimal replacement algorithm, then do this. But it's really expensive, and you're going to be wasting a lot of time, right, and resources keeping track of that queue for every possible memory read, right? So instead, typically what we do is we do LRU approximations. Okay. Least recently used approximation algorithms, right? I'm going to look at one of these in detail, and then I'm going to kind of hand wave a little bit about the other two. But this would be the aging page replacement algorithm. Aging page replacement algorithm. Give each page a reference bit. That reference bit is set if that page has been referenced. Okay? Give each frame an aging register. Okay. So then you have D total references, some number of references. And D can be changed up or down. It's usually determined experimentally. Okay. After D total references, right, take each of these reference bits. Well, first take each aging register. Okay, so after dereferencing, shift all registers, I guess, right 1 bit. Okay, shift all registers right 1 bit. And that left you a bit at the front of the age register. Put that page's R bit at the front. Okay, so let's say there are 2 registers here, and they look like, I don't know, 1 0 1 1 0 1. So 1 2 3 4 5 6. I don't know why it's 6, but let's say it is 0 0 1 1 0 1. Okay, 1 2 3 4 5 6. Okay, this guy's R is 0 after D total references, and this guy's R is 1 after D total references, which means, right, that sometime in the last D references, okay, so D keeps getting reset, right? D is a counter, right? And so it counts down from like 5 to 4 to 3 to 2 to 1 to 0. When it gets to 0, we do this, okay? So sometime in the last D references, this page was referenced, okay? So what I'm going to do is I'm going to get rid of this bit. I'm going to shift everything down 1 place, which gets rid of the least significant bit, okay? And the same for this one, which gets rid of the least significant bit, okay? And then I'm going to put a 1 up front here and a 0 up front here, right? That R bit, this R bit went to right here. This R bit went to right here. So now, all of a sudden, whereas this was a higher number before, now this is a higher number, right? So when I get ready to replace a page, I simply look for the smallest number in the aging register, right? And that tells me it's been the longest since that they have been used the least. It doesn't tell me strictly that they've been used the least overall, okay? But it like groups the family of things that have been used and those that haven't been used. So like if you've been used, you get a 1 in your most significant bit. And if you haven't been used, you get a 0 in your most significant bit. And if you get enough zeros in your most significant bit, then you got all zeros, right? And if you've got all zeros, for instance, after 5 rounds and there are 6 zeros, 1 2 3 4 5 6 in your aging register, then you know you haven't been used in the last 30, 6 times 5, right? In the last 30 reference calls to memory, okay? And so this is a good indication that you should be kicked out, okay? Does that make sense? It's not exactly least recently used, but it's an estimate of least recently used. And by the way, what if there are a bunch of zeros? Or what if there are a bunch of 0 0 1 0 1 and then there's other guys 0 1 0 1 1 0 0 or whatever, you know, and they are tied? Just pick one somehow and get rid of it. Okay? Does this prove that this one, do we know anything about this one and this one? Have they both been equally as little used? No, we don't know that for sure, right? We don't know that for sure because I don't know what happened in the past anymore. I don't care, right? I'm just looking most recently. So like there's now a window where Instead of looking for universally what the least recently used thing is, I'm looking for the least recently used thing in a window of time. Okay? And then I say, well, okay, we're going to kick you out. Right? And I might choose the one that isn't actually least recently used here, but I don't care because this is just an approximation. Okay? We can also add to that. So add to that, the previous page, this notion of using the M bit, the modified bit. And this is the part where I said I would do some hand waving, and here's my hand waving. The two other approaches to estimate least recently used are called second chance page replacement and third chance page replacement, and you're expected to read about those. So they make use of both the R bit and the M bit to give us maybe a better idea of which page to replace. Okay? Because obviously we want to replace things that have not been modified. But we want to balance that with the idea of how long has it been since you were modified, right? And that's what these algorithms attempt to balance. Okay? Questions about that? All right, so let's look at category 2 here. Yes.
When we work with fivefold algorithm, we have a term called belated anomaly.
What is it called?
Belated, B-E-L-A-D-Y, anomaly.
Spell it again, B-E-L-A?
D-Y.
Belated. This is in the book?
Some in the exercise in the 7.2, 7.2.4.
I don't know. Let me look it up real quick. Am I going to be able to remember it? Probably not. Hey, I did it.
Exercise number 7.2.4.
Okay, so 724. Oh, yeah. So this is just some dude's name. Yeah. I don't know how to pronounce it. Bellotti, I think. But that's just some guy's name. So this is asking you to, I don't know. So the number of page faults generally decreases when the number of page frames increases with first in, first out page replacement. An occasional anomaly occurs where increasing the number of page frames increases the number of page faults. That's Belatti's anomaly. Okay? So the anomaly was discovered by Laszlo Bellotti. Okay? Can you demonstrate his anomaly? Maybe you can show that anomaly just by thinking about what's going to happen. Maybe you look it up. It's fine if you look it up in this case. Yeah. Thanks for asking about that. Okay. All right. So second type. The second type would be the variable number of frames per process. Okay. So this talks to us. This introduces the notion of an optimal working set. Optimal working set. Okay. And the notion there is that it's the set of pages that will be needed in the immediate future for the process. Okay. Obviously, the optimal working set would be great if all of those pages could be resident. Right? That'd be awesome. Okay? Because if they're it's the pages that need to be in memory in the immediate future for our process to continue running. Right? If they're not in memory, if they're not resident in memory, then what's going to happen to our process? It's going to slow down because it's going to cause page faults. Okay? If our working set is not big enough, if our number of page frames is not big enough, then we're gonna see an increase in page faults. So the first algorithm under this category is the working set algorithm. Okay, and I haven't said specifically, but there's this notion of there's this notion of a reference string. And this is literally just a string of page references, okay, by frame number. Okay, we know the last however many. We can keep track of however many references we have, right? So as the references go, like I reference page 0, okay, put a 0 in the reference string. Then page 1 gets referenced, and then page 0 gets referenced again, and then page 2, and then page 3, and we fill up the reference string like so. And it keeps flowing outward, right, as more and more memory references are taking place, okay? So the working set algorithm says, let's use a window over that reference string that is D long. Okay, so I've got my reference string, and I'm only gonna have a window here that is D long. Okay, so this is the future. I don't know what that looks like yet, right? But references are going to happen. This is the past, right? This whole thing right here is the past references. And so we can think of sliding this reference frame from right to left, okay? And this is going to be a window that is D references long. And as it slides, the specific references in that D window are going to change, okay? But the simple algorithm is keep resident all the pages that were referenced in that window. Okay, pretty simple. How big does D have to be? Well, that's up for debate. Okay, that's up for debate. All right, then there's the page frequency replacement algorithm. Okay. That algorithm says that there's a set number of allowable consecutive page faults. Right? So on each fault, you obviously have to load in a new page. Okay? And, oh, sorry, again, throw something. Yeah, like stand up. Yeah, no, I don't know. I'll eventually see you, but all right, so on each fault, load in a new page. That's what we have to do for every fault. So how do I choose that? Well, we need to use one of the algorithms we talked about before. But then after a certain number of faults, right? A certain number of consecutive faults, dump all the frames that have reference bits of 0. Okay? Just dump them all. Right? All right, then lastly, we want to talk about the time and space efficiency trade-offs for virtual memory. Okay. The page fault rate is the number of page faults over a specific time. Okay. Nothing earth-shattering about that. Actually, let me use the notation that the book uses. They call that capital P, and they say number of faults over time. Okay? We want to lower that. And so the effective access time then for looking up, for accessing a memory location is E equals 1 minus P. That's this. That's the big P. So this is this. Right? Times little m. Okay? Plus P times S. All right? So what's m? M, little m, is the time to access memory. Okay? Yeah, time to access memory. And big S is the time to process a page fault. And this is accessing memory that's resident. Okay? And big S is the time to process a page fault. All right? So what this means is that 1 minus P, okay? So if P is low, right, then M takes a larger part of this than P times S. Okay? So I'd like capital P. So the total cost on this term is inversely proportional to capital P, and the total cost on this term is proportional to capital P. And so I would like to have this be the bigger part of this term, right? Than I would this. I don't want to do that. So this is just a fancy way of saying that our access time depends, the effective access time depends on shrinking the page fault rate. Okay, which is a thing we probably already intuitively knew, and certainly something that we have said so far today. So aside from making clever use of page frames and page frame replacement algorithms, what else can we do to lower that capital P, right? One thing is we can talk about load control. Okay. How many processes should be running concurrently? That's the question. And there's a trade-off. Let's look at, go down here and look at this graph. Capital L and capital S. So when L equals S, that means that the time between page faults equals the time to service the page faults, right? So L is the time between page faults, and S is the time required to service the page faults. If L, right, if L is greater than S, then we slide this little line down here and we'll find that we'll be somewhere on the upward facing curve of CPU utilization, right? We can actually increase utilization, right, by making sure that we have enough page faults, okay, that we don't outstrip this balance. But as soon as we push the number of page faults over this cliff, it falls exponentially down, okay, and gets into the thrashing, my computer can't work anymore range down here, right? So what I want to do is I want to have the number of processes running concurrently so that L equals S, or at least very, very nearly equals S, okay? So if I'm consistently spending more time servicing page faults than I am time between page faults, then I'm not optimal, right? So the optimal place is right there in the middle. This argument is, the argument here is just because I can multi-program a great number of processes doesn't mean that I should multi-program all those processes at the same time. Okay? So if I can do anything to decrease the number of processes that are running concurrently, if I'm over here on the right-hand side, then that's what I should do. Or if I'm on the left-hand side, then I should increase the load of the system. All right? The other thing is the choice of page size. How big should my page be? Now, you'll recall from last week, I think it was, we talked about how we can arbitrarily pick a page size. Well, it's not quite arbitrary. It has to do with how we organize the address space, the number of bits that we use to name our individual pages. We didn't talk at that time about what we should do, okay? And the reason why is because, and you know I love these, there's an engineering trade-off here to consider, okay? And asking you about such engineering trade-offs is a favorite thing of mine to do on the exam. That's not a hint exactly because I haven't made the exam yet, but maybe it's kind of a hint, okay? All right, so what's the pro of having large page size? Well, the pro there is that there are fewer pages overall, okay, for the same address space, a larger page size, which means that there will be smaller page tables, okay? So less space is wasted on keeping track with page tables. So the translation look-aside buffer is more effective because it covers more pages. It allows you to keep more pages in that table, right? You remember what the translation look-aside buffer is? It's when we have to do a address translation. If we have to do two translations, if they're paged and segmented, right? And the translation look-aside buffer stores just where they are in memory, okay? Just does a side-by-side. All you have to do is look it up in this table, and that's where it is in physical memory. So you have only a limited number of slots in that table, and the fewer pages there are, the higher percentage of the pages you can keep in the translation look-aside buffer at all times. Okay, so that's awesome. And the cost of disk I/O, right, actually goes down when you have bigger tables because seeking is the major bottleneck, and we're seeking less, all right, because they're all on the disk together, right? And so I just seek to the start of it and I read the whole thing. It's a big, huge chunk of memory. Okay, so actually disk IO goes down when table sizes are very large. But I get internal fragmentation when page sizes are very large. Okay, and I'm not going to go into details about what that means, but hopefully you understand what internal fragmentation is by now. The space at the bottom of the page may not be used, and the page fault rate increases because a large page contains more stuff that might not be being used. Okay, so it fills up memory, right, at a higher percentage of memory per page, right? And so if we can find ourselves in a position where I need one thing in this page, right, but it's taking up all this memory, which means that we're going to have higher page fault rate. Okay, so I have couched this in terms of the pros and cons of a large page size. But if you flipped con and pro and put small page size, then you'd be saying what's good about small page sizes and what's bad about them. They're inverses, right? So like at the extreme, we have the largest possible and the smallest possible. You really see these differences coming out. Where do you want your page size to be in the middle? Okay. Which one of these concerns are you most worried about? Where is the balancing point that you're comfortable with how big your page size is? Okay. I don't know the answer to that question. That's a rhetorical question. But what I can ask you is what the trade-offs are. All right, any questions? No? Now, admittedly, I copped to a little bit of hand waving on chapter 7. In fact, there's stuff here that I just straight haven't gone over from chapter 7 as well. Not much of it, but there are a few things I haven't gone over from chapter 7 as well. So do the assignments. Oh, and the assignments this time, the instructions are give me a digital copy somehow. And so you're not tied in. Some of you guys didn't like it, that it was a quiz last time. Okay, so if you want to write it out on a sheet of paper and scan it and send it to me, that'd be awesome. I would prefer that you not take a cell phone picture of it and send it to me, because you guys are computer scientists and you can do better than that. Yeah, but if you wanted to do like a document scanner with your phone, that's an option. Yeah. But give me a digital copy somehow. If you don't want to write it by hand and you want to put it in Word, or you want to put it in LaTeX, none of you know how to use LaTeX, or you want to put it in whatever digital format that I can read easily, don't send it to me in binary, then that's fine. I don't care. As long as I can see it and you can submit it on Canvas, then we're cool. Okay? All right, exam next week. If you got questions, while you're studying, as I know you will be, send those to me, and I'll get an answer back to you. Yes, sir.
So, sorry, I know you haven't made the exam so far, but like the assignments which we are getting, we have to solve them. So, will it be particular exercises on the exam, because then we need to like solve it on a paper or something?
Yeah. This is a good point. I don't know. I'll keep that in consideration. It might be, yeah, that's hard. It's so much easier if you come to class and write it out,
Like during COVID, like in summers, one of our math professor then he made a monologue, and we were like actually solving in front of him, and then we had to show our answers and like submit it as a scan file.
Yeah, I'm not going to do that. I'm not going to do that. That sounds like an awful lot of effort on my part. But I might come up with something. I don't know. I'll think about it. I'll let you know. So,
did you get a page on your Jamboards? I didn't get all the
Sure.
page.
These are always posted on Canvas. Did you not know that? Okay.
Yeah, I just had like the very last.
Okay.
Because you switched over
Other questions? All right, then I will not see you next week, but I will hear from you all the same.